Greetings, ladies and gentlemen. My name is Mampuele Lebepe. I'm a student from the University of Limpopo, and my presentation is about the evaluation of denial of service attacks in software-defined cognitive radio networks. Now, the following is the presentation outline. I'll start with the introduction and end with the conclusion. So, what are software-defined cognitive radio networks, rather? So, this is a network that is an integration of two networks. The first one being the software-defined networks, which is a framework that addresses several network resources management challenges. And then on the other hand, we have the cognitive radio networks, which is designed to address spectrum scarcity by implementing efficient and dynamic spectrum access. So, the cognitive radio networks provide secondary users with the ability to coexist with the primary users in non-interfering mode. All right. So what we're going to be doing is we're going to be evaluating the denial of service attacks in this specific network. Moving on to our problem statement, denial of service attacks are increasingly employing sophisticated attack strategies which cause unavailability of network resources by overwhelming the networks. Now, denial of service can cause disruption of services resulting in loss of revenue. Now, the main objective of a denial of service attack is to shut down a machine or network, rendering it inaccessible or unusable. Therefore, the result of these attacks is often lost time and money. Now, our study is motivated by the significance of security issues in modern technology, and most importantly, the need to protect communication from malicious users. Moving on to our aim and objectives. Now, the aim of our study is to simulate the denial of service attacks against software-defined cognitive radio networks, and our objectives are to compare the jamming attack defender to the SDN guard. And then our next objective is to minimize the following matrix using software-defined guard and jamming attack defender. The first one is the average processing time, the round trip time, and lastly, the signal strength. Moving on to our related works. In 3, a scheme is proposed to mitigate denial of service attack in software-defined networks using path randomization technique. Now, this study focused on minimizing the effects of denial of service on flow tables which can degrade the network switches. And then the authors used an algorithm to aggregate flows that produced a positive outcome. The authors in 4, the effects of denial of service attacks on network performance were discussed. So the study shows how the attack affects parameters such as bandwidth of the control plane and latency. So the impact on performance of controller was also analyzed, but unfortunately these issues were not addressed. Moving on to our simulation / methodology, the following table shows us our tools and parameters. We will be using MATLAB to simulate our network. Our controller is Floodlight 1.2. Our switch software is OpenFlow version 1.3. Our intrusion detection system is not 2.0.6, and our simulation area is 150 meters by 150 meters. Now, the first scheme that we are going to be evaluating is called the SDN guard. Now, the following figure shows us a rough description or depiction rather, of the SDN guard and how data is transferred in this scheme. Now, the SDN guard can be seen as an SDN application that can be plugged on top of any SDN controller, and it relies on an intrusion detection system to analyze network traffic and produce alerts when detecting a malicious flow. The second scheme we'll be evaluating is called the jamming attack defender. Now, in jamming attack, the jammer, which is the attacker, maliciously sends or receives data to obstruct genuine users in a session, right? So this situation in turn creates a denial of service condition, right? Now, the jammer may continuously send data packets so that a legitimate user may not sense the channel as idle. Legitimate users may be forced to receive junk packets sent continuously by the jammer, or may jam a radio transmission and corrupt those data packets. Moving on to our results, we examined the efficiency of the SDN guard and the jamming attack defender. So we analyzed the schemes according to the following metrics. First one being the controller input, incoming throughput, average processing time, round trip time, and signal strength efficiency. Now, the following figure shows us the average response time for SDN guard and jamming attack defender. As we can see, the red lines is for the SDN guard and the blue lines is for the jamming attack defender. So we can see that the RTT for the jamming attack defender is higher than the RTT of the SDN guard, caused by long timeouts associated with malicious flow traffic. So this prevents the switches from requesting new flows. The requests are also not sent to the controller for new entry requests. So we can clearly see that the SDN guard is a better scheme because it has lower RTT. All right. So moving on to the next set of results, we have the power spectral density for the jamming attack defender. So power spectral density, also known as PSD, is a measure of signal power content versus frequency. So this figure, as I mentioned, shows us the power spectral density of the jamming attack defender. So as the frequency is 0, the magnitude is around 17. And as the frequency increases, the magnitude decreases, and then it remains constant. Right. So now we are going to compare this with the PSD of the SDN guard. So this figure shows us the PSD of the SDN guard. At 0 frequency, the magnitude is at 17. Now, as the frequency increases, the magnitude starts decreasing. This means that the jamming attack defender has a better PSD because it remains constant while the PSD of the SDN guard decreases. So therefore, jamming attack defender has better signal strength than the SDN guard. Right. Moving on to our next set of results, we have the average processing time for the SDN guard. So we were investigating the average processing time of the SDN guard versus the average processing time of the jamming attack defender. Now, sampling rate reduces the intrusion detection system workload, which reduces the packet processing time of the intrusion detection system, right? So it relates to the amount of time it takes an intrusion detection system to analyze a packet, and the following figure shows us average processing time for the SDN guard. So when sampling is not considered, the average processing time is about 14 seconds. The sampling rate later decreased to 10.5 seconds, and thereafter gradually as the sampling rate increases to 80%, which means that as we increase the size of the sample, the processing time decreased, which shows that the SDN guard can process a large number of packets at a faster rate. Now, the following table shows us the average processing time of the jamming attack defender. So without traffic, meaning 0% sampling rate, the intrusion detection system receives all the network traffic, and the average processing time is about 23 seconds, and then it gradually decreases to 19.5 seconds as the sampling rate decreases to 80% with the jamming attack defender. It also means that as we increase the number of packets, the processing time decreases. So looking at those two figures, we can conclude that the SDN guard reduces the packet of processing time more than the jamming attack defender, which means that the SDN guard is a better scheme than the jamming attack defender in terms of processing time. So in conclusion, we have also examined the use of sampling techniques to reduce the amount of mirror traffic sent to the IDS from the switches. So we have observed the SDN guard reduces the mirror traffic more than the jamming attack defender. We also observed that in terms of RTT, the SDN guard takes less RTT than the jamming attack defender. The PSD of the jamming attack defender is better than the PSD of the SDN guard. So overall, the SDN guard is a better scheme in mitigating the denial of service attacks in software-defined cognitive radio networks. These are a list of my references, and I thank you.